Hi guys, and welcome to this video on performing a regression analysis. Yes, this is a continuation of the Further Maths Units 3 and 4 videos that are dealing here with least squares regression lines and all the excitement that comes with it. Now, obviously, this is now my third video. Previously, we've looked at why we use least squares regression lines and how to use both the formula and your cares for least squares regression lines. Now we're going to perform an analysis, and I love this particular section, but it is absolutely huge in this course. Why? Because we're going to use it in stacks. There'll be probably elements of this in exams. I cannot downplay or in fact overstress the importance of this particular video and those that will follow it. So I'm about to start, but if you haven't already done so, if you could do me the greatest of honor of subscribing to my YouTube channel, that'd be great. Never going to be rich, never going to be famous, but at least I know that people are watching it if you subscribe. So thank you so much if you can do that for me, and also spread the word. And if you haven't already known, maffsguru.com, there is a link on the page now, is where these videos can be easily sorted, searchable, with downloadable notes, etc, etc. So hopefully head over there, sign up for free, and enjoy the maths that is available. Okay, so performing a regression analysis, as I say, I always normally start with a bit of a recap. We've looked at least squares lines and what they are. Now I think of those as basically lines of best fit. We're going to take data from a scatter graph or a scatter plot, and we're going to try and find some sort of line of best fit that'll either be positive or negative, and we'll be able to use that to predict. The whole point of this is to be able to predict values. But be careful, because there are these things called residuals and all of the excitement that goes around it. And if you haven't got any clue what I'm talking about, please head back to the previous two videos where I explain it to you, such that maybe some of this will make sense. Okay, I love a good recipe. Am I any good in the kitchen cooking? I should cocoa not at all, okay? Put me in the kitchen and I have no idea what on earth is going on, and probably couldn't even turn the cooker on. That's how inept I am, but hopefully it's because I'm recording videos. The recipe of success is shown above or behind me, and literally it says those 8 points should be able to give you 100% in every single regression analysis you could ever possibly do, so long as we follow the recipe that it is given. So number 1 is construct a scatter plot to investigate the nature of an association. Number 2, to calculate the correlation coefficient to indicate the strength of the relationship, and so it goes on. So what I'm going to do in this video is I'm going to take some data provided to me by the Cambridge Further Maths Units 3 and 4 textbook. Thank you, Cambridge, for allowing me to use your examples. And I'm going to step through this line by line by line to give you an understanding. The next video is effectively going to take that data again, and we're just going to do it twice. Right, so fingers crossed, by the end of this, you will be a gun. As I say, the notes are all downloadable on maffsguru.com, so head on over there later on when I upload this video. Right, so first things first, as I say here, we always need some data to be able to work with to help us find a regression analysis, and they have to be numerical data. Both of them must be numerical data, so that we can draw out a scatter plot, and from that we do our regression analysis. Okay, so what do we have here? We have age and price in dollars. Now, luckily, the question has told us somewhere that age is our explanatory and price in dollars is our response. Okay, so I think this has something to do with the price of cars. If I remember, it's about how as age increases, the value of the cars decrease. So first things first, construct a scatter plot. So I'm going to go through this step by step by step. And step number 1 says construct a scatter plot to investigate the nature of the association. All right, so we can use a CAS. I'm going to fire up my CAS, and there we go. Now, as you can see, what I have here is the screenshots below of my actual steps that I'm going to do, because when you download these, you should have something nice and easy to understand. So there's my data, and it says construct a scatter plot. How do we do that? Well, I'm going to hit this little button here, and I'm going to say, please, please, please draw me a scatter plot. And I want my age along the bottom, so I'm going to go main age along the bottom, and I'm going to go price up the side and set. And yep, no scatter plot, because I now have to say, okay, can you draw me all the graphs that we need? And there we go. Lo and behold, there is my information. Now, if I wanted to, I can actually resize that bottom one, and there we go. Now, I don't know, on these CAS calculators, particularly this Casio ClassPad, while I can seemingly get the values along the bottom, I cannot get the values up the side to show on this calculator at all. If you know how to, leave a comment below and I will give you a credit in a later video. But at this moment in time, I don't want to resize it. I'm going to go back because step 1, construct a scatter plot. Now, in some exams, in some SACs, you may be asked now to sort of draw that scatter plot. You can't do it accurately. You can probably just do a pretty accurate sketch, but that is part one done, tick. From the scatter plot, we can see that there is a negative linear association. So the whole point of doing this is for me to have some idea of whether this data is linear. Because remember, I can only do a regression analysis if my data is linear. Okay, so we know it's negative because it's sloping down. We know it is weak. But is it weak, moderate, or strong? That's the question I'm trying to ask myself. Well, how do we go to know that? Well, let's move on to step 2. And step 2 says, calculate the correlation coefficient. So I'm just working my way down this recipe. So calculate the correlation coefficient. How do we do that? Well, if you remember when we do a linear regression, then what do? We get the values that we need. So first things first, I'm going to go back up, click on this top section here. So my blue line is around my data. Calc, regression, linear regression. We have to tell the calculator, once again, they've got age on the bottom, price up the side, and click on OK. And piff, puff, poof, up comes the values which I was expecting. And as we can see highlighted here, we have an R value of 0.964258. So there we go. I now have an R value of 0.96, which if you remember, I can go back to that table we had previously, that graph we had previously, the little one that tells you whether it's strong or moderate or weak, and just read off the value. So having done that, apparently I can now describe my data as a strong negative linear association. The strong has come from that value of R. Negative we just saw because the graph was sloping down, and linear, well, obviously we could see that pretty much those points were in a form of a line. They definitely weren't curved. So let's click OK, and on my calculator up comes my linear regression. So we now have the first part of a report. And I'm going to deal with this step by step. There is boilerplate sentences that you just change the values. And again, you should be able to ace every single one of these sections by using the boilerplate code or the boilerplate sentences. So we now have the first part of the report. So reading this off, there is a strong negative linear association, thank you very much, between the price of these second-hand cars and their age. And my advice is always, where you can, put in values. We know that we had a value of R. It came out to be minus 0.964. And there we go. We put it in. Better to have slightly too much information than too little. But we do not want your life stories, ladies and gentlemen. You have to be very careful you don't write too much. Okay, so that was step 2. Number 3, determine the equation of the regression line. Well, I've already had that information. We got it in this screen already. Oh, let's not highlight that one. Let's go back. We had it in this screen already. And if you remember, we have y equals a plus bx, where a is my intercept and b is my gradient. Okay, so we can write that in as y is equal to 35134 minus 3935 times x. That's correct, yes? Nope. Because again, we have to be very, very careful with what we write our formulas. Our formula or our regression line has nothing to do with x and y. That's just the calculator or us trying to fit things in. And do I know what is on my y-axis? Yes, I do. If you remember, it was price. And what's on my x-axis? It was age. And so these are the values you'd be expecting to put in as my x and y. Okay, so also be very, very careful to make sure that you have your calculator in a plus bx. All right, if we have it the other way around, ax plus b, you might put the wrong values in the wrong place. So my advice is make sure your calculator is always there. Rightio, ladies and gentlemen. Hence our equation of our least squares regression line using that formula gives me price equals 35134 minus 3935 times age. Now the question will generally tell you what order of magnitude to sort of round this to, whether sig figs or decimal places or just to the nearest whole number. So please make sure that you use or read the question. And so we have our age as my explanatory variable and my price as my response variable. Tick, we now have my equation. Thank you very much. Step 4, interpret the coefficients of the y-intercept and the slope of the least squares line. It is so important. in your report that you realize we are doing this for you to interpret the data. Sadly, you're not going to get a lot of marks for just plonking a load of stuff in a calculator and just proving that you can use your calculator. Okay, we're actually here to test do you understand why you are doing this stuff. Okay, so we don't want you to regurgitate it. We now know that the gradient is important because what it means is for every 1 unit increase in that particular item there, right, or for every 1 unit increase in our explanatory variable, then there is going to be this, including the plus or the minus. Now the plus simply means there's an increase. In this situation, we have a minus, which means that's a decrease. So what we're going to say is for every 1 unit increase in my age, there is going to be minus 3940 in price. And that's literally what you've just got to say in terms of a sentence. And so as I say here, this means for every increase of 1 year in age, the price of the car will reduce by $3,940. And again, remember, we've got to make sure that we have the actual variables they give us. Age, price, don't forget that. Okay. What else did we need to know? We needed to know about our intercept. Yes, and again, understanding what our intercept means so that we can write about it sensibly is of course important. What does it mean? Well, if you remember, our intercept is always the point where the x value is 0, okay? Doesn't matter what it is, explanatory, whatever. Our intercept is only true when this value here is 0. And lots of questions will try and trick you. They'll start with 20 or 200 or whatever else. It's not what the intercept is. That value on that graph is not the intercept. It is only the intercept when we have 0 here. This value there would be my intercept. And so, because we're dealing with age of cars, we would then turn around and say, when the age of our car was 0, now we're not going to say the age of our car is 0, so we could say when our car was new, because that would suggest it was actually age 0, then its price was, and probably 35,100. Yes, so again, we can write something like when the age of the car was 0 years or new, the price was $35,100. Okay, cool. We haven't really done too much maths, have we? We've just used that calculator. We're just now interpreting our results. Step 6, use the regression line to make predictions. The whole point of the regression line is to make predictions. Yes, that's all it's there for. So, the question probably would have gone on, and maybe the SAC or the exam would have said, okay, well, what would the price of the car be, which is 5.5 years old? Well, that's fine. We can do that. It's asking us to find a price by giving us an age. We've got a formula, so we can literally just bang in that value for the age and get our price. Now, I'm not going to do that on my own calculator because I've already got it here. But let's keep the formula in place. 35,100 minus 3,940 times 5.5 gives me the wonderful value of 13,430. So that means my 5.5-year-old car would predict to be $13,430. Everything I'm saying, I'd be looking at writing down in a report succinctly in the best way possible. And as I say, the good news is there are generally boilerplate code or sort of sentence structures that you can use. Now, Walling Will Robinson, the Further Maths exam, loves asking about whether your data is a prediction and it's a good prediction or a bad prediction. And this is very much talking about the idea of interpolation and extrapolation. So make sure that you fully understand the difference. I'll scroll over here and just do it one more time. Here we go. Let's assume that this is my line of best fit. Now, our data values may be all over here. I'm just going to make this up for you at this moment in time. So what we can now see is this value here is my smallest data value. That's my smallest, in this situation, age that we have details of. Here, my biggest age that we actually have real data for. If I now want to find the price of any car between my lowest age and my highest age, anywhere in this bit here, then we now say that the prediction could be or would be a good one. Why? Because it falls in between that data. So in other words, that is called interpolation. If you are looking for a value of a car, if you are falling for the value, or if you are looking for the value of a car outside of this, so say we were looking for the value of a car here, then because that falls outside of the data I was given, that range of data I was given, we don't actually know where that cross would be. We would hope that it would be somewhere around here. But to be honest with you, outside of this point here, my line might do something like this. You don't know, highly unlikely to be that, but you just don't know. So we generally say that anything that has data items which fall outside of our interpolation is called extrapolation. And in which case, our formula would not necessarily be a good prediction because we only created that formula between the 2 points that I had. Okay, so back to my recipe. I'm going to say step 5, use the coefficient of determination to indicate the predictive power of the association. That's a lot of words for turning around saying what percentage of variation in the response variable is explained by the variation in the explanatory variable. Okay, that's easy. We love that. So we know that the coefficient of determination has a formula, and it is given by that formula here, the correlation coefficient squared. What on earth is correlation coefficient? It's the Pearson's correlation coefficient, which gives us the value of R. Oh, hold on a moment. My calculator had already given me that value of R. Whee! And so all I've got to do is to go to my coefficient of determination. I'm going to take my value of R and square it. We knew the value of R was given as 0.964, or we read it off our calculator. I squared it, and that gave me 0.930, which, remember, I have to express as a percentage. So you always take that decimal number there, 0.930, times it by 100, and then get your answer. Now again, I have seen in a lot of exam questions, they will ask you to round to a certain number of decimal places. So do not round too early. Do your calculation, multiply your R squared by 100, and then round it, or you could lose marks for accuracy. Right, so having worked that out, do I have boilerplate code, or is there a sentence structure I could use? I should go and listen, this one here, all right? So I'm highlighting almost word for word. The only thing you need to change is in fact the stuff in bold, or the bit I'm now gonna highlight. So what does it say? It says the value of the coefficient of determination suggests that 93%, there we go, of the variation observed in price in dollars, that should really be in bold, can be explained by the variation in age of the car. Exactly what we did previously. Step 7, we are powering through this. Calculate residuals and use a residual plot to test the assumption of linearity. Now this is actually new information. So this is actually new information. If you remember from what we had before, here is my line of best fit. Remember, that is a prediction. Our actual values could fall all over the place. My calculator has just done some funky maths to allow it to find this line of best fit to predict. But you have to remember, this here is my actual value of that data point. Whatever falls on this point here is a prediction. And if you remember, if I zoom in nice and big, then the difference in height between the actual and the prediction is called my residual. All right, so my residual. Other people think of this as an error, all right? So it's sort of my size of my error away from my actual point and my predicted point. So let's try and find an example of one of our residuals and then work out how we can use all of that. So we know, as I said earlier, that our residual value is given by our actual data value minus the predicted value. And so let's use our example. What if we want to find the residual value of a car that is 6 years old? Well, we already know that we have a data item for 6 years old, so 6 years old, that told us the actual price was $6,500. But what would my equation predict? Yes, remember, our equation is predicting. So taking our value of the equation, or our equation of price is equal to 35,100 minus that, I am going to change this age here for the value of 6, which is what I've done using my CAS calculator. And what you can see is it predicts the car as 11460. Well, hold on a moment. we actually had an actual price here. So this prediction and our actual price, there is an error, all right? There is a residual. So we can now suggest that our residual value is given by actual data value minus our predicted value. Well, we know what the predicted value is. It's 11,460. Our actual data item value was 6,500, which when we took away our predicted value gave us a residual of minus $4,960. Okay. So this means the value of the car is roughly speaking $5,000 less than we would have predicted. Okay, so that's important as well. The actual value of the car is roughly $5,000 less than our prediction, hence there is an error. So testing the assumption of linearity, what we're going to do now is we take all of those values, we take all of those residuals, and we're now going to get the calculator to work it out and add a column to our spreadsheet. How do we do this? Okay, well, I've left my calculator open for a reason. Just going to close that screen for a moment. And if I go back and say calc, regression, linear regression, and we'll go back and we'll say, well, we know along the bottom here we wanted age, and up the side here we wanted price. Now, normally we'd have told you to leave the other boxes, but what do we notice here is we see a copy residual is off. Now, if I turn that on, it actually is going to ask you, right, where do you want me to put the values of the residual? And you're going to go, huh? Well, we've already got two columns. We've got age in one column, we've got price in another, and so the next one, we can get the calculator to autofill. Well, list 1 has been taken, list 2 has been taken, so let's tell the calculator to use list 3. I'm going to click on OK. It's going to come up and do the residual, the analysis for me. It's going to do the same thing, but I'm going to close that down, and what do you notice about all of my values here? Well, yes, welcome, ladies and gentlemen, here are my residuals. Now, what do you notice? I've just highlighted a value there that says for the 6-year-old car, the residual was minus 5,023. But that seems to go against the value I got slightly earlier of 4,960. How on earth could that be possible? Well, this is where we hit problems with rounding. Remember, all of the stuff we did previously with this formula, with our formula from before, there we go, was where it had actually rounded those values. So we needed to be very careful that anything we then come up with will actually be slightly off. So that's why it's important to make sure that you use the values of the exam or the SAC tells you, but also to realize that our residual plot may also give different values than we're expecting. So we've now got our residuals in list 3, and what are we being asked to do? Well, the question said, draw a residual plot. What is a residual plot? Well, funnily enough, it's a scatter plot, but with age on one column, and age on that column, and now our residuals on this one. So how do we do that? Well, if you remember, I'm going to click this graph here, scatter. We're going to keep age on my X list, but on my Y list, I'm actually going to put list 3. Click a set and draw the graph, and lo and behold, up comes a load of dots. Now, I want you to realize, or just see this little thing here. That line here is because when I click on here and go set graph, it'll say draw on my previous regression. I'm actually going to take that off, and I'm going to draw the graph again, and that little line will go, just in case that comes up on your calculator. Now, what on earth does doing this residual plot have to do with the price of fish? Funny enough, it has nothing to do with the price of fish, but it does have everything to do with the assumption of linearity. And the textbook states, and it's one of those things you just have to accept, that linearity is assumed, and I'm just reading off the screen here, linearity is assumed when the residual plot has no clear pattern. Essentially, they are randomly scattered. And as far as I can tell here, if we were to look at these points here, they seem to be randomly scattered. Now, you can turn around and say, oh no, I can see a bit of a shape. That's irrelevant. What you'd be looking for is if it is not linear, the points for a residual plot will either do some sort of curve like that or some sort of curve like that. Because it doesn't, we then can say, we now, having drawn my residual plot, can assume linearity. Will you have to draw this in an exam? Possibly. In a SAC, more than likely, you'll have to give evidence by drawing a sketch of this. And ladies and gentlemen, believe it or not, we've done pretty much all of the hard work now. So I'm going to put my calculator down, and realistically speaking, we're just going to tie all of that together now and write our report. And we've already done the hard work step by step by step. So here is a suggested report taken from the Cambridge book. 1. From the scatter plot, we see that there is a strong negative linear association between the price of the second-hand car and its age. Hold on a moment, that came earlier. Yes, it did. The only thing I've added now is that there are no obvious outliers. It is always a good idea to talk about outliers, and in this situation, there were no obvious outliers. The equation of the least squares regression line is, so we've written our equation in, the slope of the regression line predicts that, blah, 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 and the intercept predicts that, blah, blah, blah. So again, this has all come from this recipe step by step by step. The coefficient of determination indicates that. Again, we did that earlier, that sentence was there. And finally, the sentence that maybe we should have written in the previous section, but we're certainly going to write now, is the lack of a clear pattern in the residual plot confirms the assumption of a linear association between the price and the age of these second-hand cars. And ladies and gentlemen, there we go. As far as I'm concerned, if you use that recipe step by step by step, and write a report as clear as that with information and numbers where you can, I don't see how you could go wrong. Now, as I tend to do at this time, I tend to go through VCAR examination questions. And ladies and gentlemen, here we go. Let's go through some VCAR questions now. A scatter plot below shows the wrist circumference and ankle circumference, both in centimetres, of 13 people. A least squares line has been fitted to the scatter plot with ankle circumference as the explanatory variable. The equation of the least squares line is closest to. Okay. So first things first, what do we notice? We noticed our wrist circumference is our, well, that's the one we're going to try and predict. So my formula would have to start with wrist. So anything that starts with ankle, as far as I'm concerned, is hogwash. Thank you very much. Now, what am I going to do there? Well, the next thing I'm going to discount is basically this value here. And this is what I talked about earlier in our video. So many people believe that if a line crosses the y-axis, that there would have to be the y-axis intercept. It does not. The only time that value there is the intercept is when it starts at 0. And what do you notice? This graph here starts at 21. So you cannot read this value off as 17.4 or 17 point anything, because that is not my intercept. So D and E are no longer answers. B is my correct answer. Now, the shame of it is there will be people out there who would have looked at this question and tried to plot each of those points in a regression analysis. They'd have fired up their calculator. That's not what it was asking. Realistically speaking, it was just checking to see whether you understood that value there had to be 0 to read off the intercept. Okay, question number 9. When the least squares line on the scatter plot is used to predict the wrist circumference of a person with an ankle circumference of 24 centimeters, the residual will be closest to. Okay, so we now know that we have a formula that says wrist is equal to 10.2 plus 0.342 times my ankle. So that's my formula, that's my prediction. What did we say? The least squares line on the scatter plot is used to predict with an ankle circumference of 24 centimeters. So there's 24 centimeters ankle circumference. So I'm going to do 10.2 plus 0.342 times my ankle of 24. Bring up my calculator. Let's vidget over here for a moment just to give myself some room. I'm going to go to main, and what did we want? So we want 10.2. And we're going to do plus 0.342. Oh, no. Trying to use my fingers. 342. And we're going to times that by 24. And then we're going to hit enter. And we get our wrist of 18.408. Now remember, to work out our residual, we need the actual minus the prediction. So we know our prediction now is 18.408. What is our actual value? Well, we need to look for 24 centimeters and read off what this value was. Well, that value seems to, let's zoom all the way in, have come out as 17.1, 2, 3, 4, 5, 6, 7. 17.7. Okay. Well, way too small. Let's make that a bit there. So this is now going to become 17.7. Fire up my calculator. And we're going to do 17.7. We're going to minus from that 18.408. Now, from what I remember, the question said is closest to. So we're looking for the value that is closest to minus 0.708. And in fact, the only one there is answer A. All right, so A would be my correct answer there. See what happens? You have to work out the residual by doing the actual value minus predicted value. That was actually quite a funky question, if not a little bit long. All right, so let's get the screen back. And moving on to the 2018 paper 1, we got some information here about resting pulse rates in beats per minute and the time spent exercising in hours per week. Using this least squares line. I suppose first thing is, what are we meaning by least squares line? Well, they've already drawn that on for me. Dankeschön. There we go. We have that as our least squares line. Look for the residual for the student who spent 4 hours per week. All right, okay, so this is again, our residual value is given by my actual value minus my predicted value. So we are looking for 4 hours per week. So here is 4 hours per week. There is my actual value, and there is my prediction. So my actual value worked out to be 63. My predicted value was 64. Take those one, gives me -1, and there we go. So B would be my correct answer as -1 beats per minute. Awesome. Question number 8 says the equation of this least squares line is closest to. And again, hopefully this is similar to the question I did slightly earlier. So first things first, what is my explanatory variable? What is my response variable? It is the resting pulse rate. Oh, they all start with resting pulse rate. That's annoying. Okay, so the equation of the squeeze line is closest to, it starts as 1. So 67.2, I'm going to get rid of all of those at 67.2. It can't be that one, it can't be that one, and it can't be that one. Remember, this value here has to start at 0 for us to be able to take that value there. So we're down to 2. The resting pulse rate is. Okay, so now it comes down to us actually working out our gradient. All right, so the gradient of this is where you take 2 points, yes? And what we're going to try and do is take 2 points that actually cross on the line. So we have a point there that seems to cross through. And we also, do we have another one that seems to cross through? Not particularly nicely, no. And so we're going to maybe take this value here. So I have 2 coordinates there. I have 1, 67.2, and I have 4, 64. Why does that make any difference to me? Because I can now use that to find my gradient. And I know my gradient is y2 minus y1 on x2 minus x1. So using my CAS calculator, let's fire that up and bring it over and see what actually happens. So calculator, bring me up the keyboard and a fraction please, and we're going to do 64 minus 67.2, and I'm going to divide that by 3 because I can do that in my head, which is minus 1.06666, which basically seems to suggest that D is going to be my correct answer. Now, there may be other ways in which you can do this question. If there is, leave me a comment below if you are still watching. In fact, show me some love below anyway. Just say, hi, Maths Guru, how you doing? And ladies and gentlemen, it would appear that there is the end of this lesson. Now, I know those VCAR questions didn't necessarily have anything to do with a regression analysis or least squares lines. That's going to come in a later video where I'm actually going to run through a full-on regression analysis with data transformed, blah, 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 blah. All right, but I'm pretty much done for this lesson. And so yes, there we go. We are at the end of our performing a regression analysis lesson. Thank you so much for watching, ladies and gentlemen. Hopefully it has been useful. If it has, show me some love below, as I've just said. Say hi, say good video. Let me know what you want improved. There's another video coming shortly, or it'll drop probably tomorrow if it's not already live, on mathsguru.com and on YouTube. If you haven't already done so, can you do me a favor and subscribe and let your friends know that I'm out here? But otherwise, it has been a pleasure spending some time in your company today. Have the most amazing day, and hopefully I look forward to seeing you in a next video. Take care. Bye-bye.